Hello guys, this is the Med Dude and today we're doing Edexcel IAL Chemistry Unit 1, January 2022. So let's get right to it. Question number 1. So element X is in group 2 of the periodic table and element Y is in group 7. X and Y are not symbols for the elements. What is the formula of the compound formed between X and Y? Okay, so let's take an element from group 2. So let's say we're taking X as let's say calcium ion, so that's 2 plus, right? Let's say for Y, let's say we take our chlorine ion, which is Cl minus. So the ionic compound that forms between the two elements would be CaCl2, right? Because the 2 plus cancels out the 2 negatives. Okay, so that means that we should get X, Y, and 2 here. So that's our answer for part A. So I'm going to do, so that's not A, not B, not C. So that's C. Part B says, under what conditions does the compound formed from X and Y conduct electricity? So the compound over here is what? It's an ionic compound. Now, what do we know about ionic compounds? They only conduct electricity when they're molten, which is another word for the liquid, or it's an aqueous state. Okay, so let's see what we have here. So part A is, so option A says solid state, so automatically no. Solid state, no. It doesn't conduct electricity in the solid state, so C also no. So just by the process of elimination, we know it's D. Alright, so now we have question number 2. So which of the following compounds would you expect to have the highest melting temperature? So we have A, NaCl, B, NaF, C, KCl, and D, KF. Now, to find out what the highest melting temperature would be, we need to realize that the compound are between what? Between cations and anions, right? To have the highest melting temperature, we want the most electronegative anion. So which in this case is what? It's F, right? It's the most electronegative anion here. So we can cancel out the Cl, the chlorine compound, so that's gone. Then we look at Na and K. Now Na and K. Now Na is Na, which is sodium. Sodium has a smaller ionic radius, so it will be harder. So when we have this Na molecule, and then we have this F, right, and we compare it to K, which will be a slightly bigger, and this will be slightly bigger as well. You can see that this will be harder to break the bonds. The ionic break the ionic bond. Okay, so for that reason, it has to be NaF. Okay. So question number 3. A drop of aqueous solution of green copper 2 chromate is placed in the center of a strip of damp filter paper. The ends of the filter paper are connected to a DC power supply. What is observed after a few minutes? So if this is a matter of memory, if you remember, you can see that the chromate, right? The chromate gives off a yellow color, and the copper 2 gives off a blue color. So what's going to happen is that this yellow will be attracted to the positive end, right? And the blue, because it's positively charged, copper 2 plus, will be attracted to the negative end. Okay, so let's see what's over here. So a green color is observed to the negative end. No, green color is split to yellow and blue, because yellow and blue make green. So a yellow color has moved to the positive end, so that's correct. And a blue color has moved to the negative end, and that's what we have here. So the answer has to be C. Number 4. Which of these isoelectric ions has the smallest ionic radius? So we have N3 minus, F minus, Na plus, and Al3 plus. So we need to understand that the size of the atom decreases as we go, as the charge of the ion becomes more positive. So when we have Al3 plus, right? Now because it's 3 times the positively charged, its ion is going to be ionic radius will be much smaller, significantly smaller than N3 minus. So for that reason, it has to be D. Question number 5. Which properties of a cation results in the greatest polarizing power? Now the greatest polarizing power, just to remember, is it's always smaller radius and larger effective nuclear charge, or larger charge in this case. So, and we can, okay, so let's see what the answers are. So we have large radius, large charge. No, we don't want large charges. It won't polarize as much. So large radius is not there. And we want what? We want a large charge as well. So large charge is there. We don't want small charge. We want a large charge, and we don't want small charge. But we do want a small radius. So small radius and large charge, which is D. So the answer has to be D. Now similarly, in the question number 6 says, which properties of an anion results in it being the most easily polarized? So it has to be similar to what we just did, just a difference, right? So instead of having a smaller radius, right, we're still going to have the larger charge. Larger charge always helps, right? Larger charge always helps. But instead of having a small radius like we had initially for the cation, we're going to have a large radius. Large radius. So in this case, large radius is different and smaller radius is the only difference. So we want what? We want large radius and large charge. So large radius, large charge, that's A. And we don't have to look at the other choices. Okay, so question number 7. We have to look here. It says, what is the ionic equation for the reaction between aqueous solutions of barium nitrate and sodium sulfate? Okay, so so let's write it down. So we have barium nitrate. So barium nitrate is BaNO3, and that's twice, plus Na2SO4, and we get, what do we get? We get barium sulfate, so BaSO4 plus 2NaNO3, sodium nitrate. Now this is a barium nitrate plus sodium sulfate. Now from memory, we need to remember that sodium nitrate is actually insoluble, right? So the ionic equation in this case has to be between the barium ions and sulfate ions. So it should look like we should have Ba2+, obviously aqueous, and we should also have SO4 2- sulfate ion aqueous to give us BaSO4. So do we have this? Let's see. Is it A, Na+? Nope, not sodium nitrate. BaSO4, but we know Ba is 2+ charge because it's in group 2, so that's wrong. And C, Na2+, no, we're not talking about sodium nitrate here. So D, Ba2+ aqueous plus SO4 2- aqueous gives us barium sulfate solid. So that is indeed the answer. Question number 8. Which of these molecules are not polar? Okay, so we have our carbon dioxide, HCl, H2O, NH3. Now, another way of looking at this question is, which of these molecules are polar? Let's look at which of them are polar. Right? So CO2, so let's say I don't remember CO2. Right? I don't remember CO2. So I don't remember whether this is polar or not. Let's look at HCl. So HCl, and then H2O, so O, H, H, and we got NH3. NH3. This is not 3D, but it's supposed to be 3D. So we know that HCl, that we know this has a partially negative charge, partially positive, so that's polar already. And same thing with water, we have partially positive, and partially negative. So H2O is also polar. So what about NH3? Same thing, it's also partially negative, it has the lone pair here, and partially negative, this is partially positive, all of them partially positive, partially positive. So the process of elimination, we can conclude that carbon dioxide is not polar. Now if you remember that, obviously then you know it's carbon dioxide, but let's say you didn't remember it, this is what you should do. Check which ones are polar and then cross them out. Question number 9. The concentration of nitrogen dioxide in a sample of air is 0.5 parts per million. What is the percentage of nitrogen dioxide molecules in the sample of air? So we know it's parts per million, right? So it has to be what? It has to be 0.5 divided by a million. That's the parts per million. That's 6 zeros. And then because it's a percentage we want, we times by 100. Times by 100. And this, when you put this in the calculator, we will get 0.00005%. So what is that? That is in the question part, that is option C. So option C is the correct answer. Question number 10A. So we have ethane reacts with bromine. Ethane reacts with bromine in the presence of UV radiation or ultraviolet radiation. What is the equation for this reaction? So if you recall correctly, we always get what? We get HBr in this reaction. Why? Because Br to Br breaks homolytically. So what happens is homolytically to get no, not homolytically, sorry. So it breaks apart and we get HBr. So this breaks apart to get HBr. So the reaction should have at the end a product should be HBr. So there's no HBr here, no HBr here, no HBr here. There's HBr here, so it has to be B. The ultraviolet radiation is needed for what? It's needed for what we just said, homolytic breaking of the Br to Br bond. So that is A. Now let's move on to question number 11. So all alkanes have the same what? So do they have the same empirical formula? No. Do they have the same general formula? That's what I think is right. So CnH2n plus 2. So that's something I know is correct. Same molecular formula? No, because we have, let's say we have CH4 is methane, and then we have C2H6 is ethane, and that's obviously not the same. They're not the same. So not molecular formula. What about structure formula? Same thing, they're not the same. We have CH4 here, and then we have CH3 as our structure formula. You can see that these are not the same. Not the same. So it has to be B. Now we have question number 12. A single molecule of decane, C12H2 is cracked. Which of these mixtures could not be formed? So what happens when we crack an alkane? Well, what is produced? So we know what's produced. It produces what? It produces an alkene. Short chain alkene, no, just alkene and alkane, right? But it needs to all add up to C10 and H22. So let's look at, so pentene, we have pentene, so that is what? So pentene is what? C5H10, and then we have pentane C5H12. Okay, so we have how much? We have 5 carbons, so that's 10 carbons. And what about the hydrogens? We have 10 hydrogens here, 12 hydrogens here, so that's 12 hydrogens. So this can be formed, so that's out of the equation. Let's look at ethene. So we have ethene, so that's what, C2H4, so C2H4. Then we have butene, so that's what, C4H8. And then we have what, butane, C4H10. So now let's look at the carbons. We have 2 plus 4 is 6, 6 plus 4 is 10, so we have 10 carbons, so that's already there. What about the hydrogens? We have 4 plus 8 is 12, plus 10 is 22, so that's 22 hydrogens, so that can be formed, that's 22. So that's also out of the equation. Let's look at C. So we have propene, so propene is what? Propene is C3H6, propane is C3H8, and butene is what we did before, C4H8. Let's look at this. 3 carbons plus 3 carbons, 6 plus 4 is 10 carbons, so 10 carbons. What about the hydrogens? We have 6 plus 8 is 14, 14 plus 8 is 22, so 22 hydrogens. So this can also be formed. So C is also out of our options list, so it has to be D. Move on to question number 3. So how many structural isomers does the formula C3H6Cl2 have? Okay, so let's say you don't remember how many structural isomers you have. You can also draw it out, right? So let's say we draw the normal. Let's draw a long chain. The longest chain we can find. So we have C. You know, C. How many? 3 carbons. So let's say each end has a chlorine. Okay, so that's one. That's one possibility, right? And everything else is also a hydrogen. And then we have, let's say, C, and then it's on either end. So that's one possibility. That's 2, right? That's 2. What about if we add our chlorine in the middle, maybe here? Let's say we add it here and here toward the end. So it'll look a little like this. So Cl. So that's the third isomer, structural isomer we can think of. What about another one? Is there another one we can think of? Is there another one? What if it's attached to the same end carbon? So C, but this is Cl and this is also chlorine. So that's how many? How many are there? That's 4, right? So 1, 2, 3, and 4. So 4 structural isomers of this formula. So question number 14. The equation for the complete combustion of hexane is shown. So we have C6H14 plus 9.5 oxygen molecules plus 6 carbon dioxide. It gives us 6 carbon dioxide and 7 water molecules. So how many molecules of carbon dioxide are formed when 2 times 10 to the power minus 3, which is what? Which is 0.002 moles of hexane undergoes complete combustion. So we have 0.002 moles of this, and we want to know how many molecules of carbon dioxide are formed. So we want to know how many molecules of carbon dioxide. So we can see there's a 1:6 ratio here, right? So how many moles do we have of carbon dioxide? So we have 6 times 0.02. So 6 times 0.002 gives us 0.012 moles. So 0.012 moles of carbon dioxide. They've given us the Avogadro's constant. So how do we work out how many molecules? It's simple. Just the moles, 0.012, times the Avogadro constant L. So times by 6.02 times 10 to the power of 23. And this gives us 7.224 times 10 to the power of 21 molecules. So this is what we get. Is there any answer that's similar? Let's look. 1.2, no. 7.22 times 10 to the power of 21. Yep, that is it. That is what we want. And the rest are obviously incorrect. Moving on to question number 15. Which pollutant cannot form when alkene fuels are burnt in car engines? Okay, let's think of, let's say you don't remember which pollutants. Let's think of which pollutants can form. So just by remembering, we know that soot can form, right? So carbon particle, this soot, right, that can form. And we know that incomplete combustion also causes carbon monoxide to form. And we also know that sulfur dioxide can also form from the car engines. So what cannot form? Just by the process of elimination, we have concluded that hydrogen chloride cannot be formed by car engines. Alright, so moving on to question number 16. So iron 3 oxide is reduced by hydrogen in a two-step process. So it goes from 3Fe2O3 plus H2 to Fe3O4 plus water. This plus hydrogen gives us iron. They tell us that what is the maximum mass of iron that could be produced from 39.9 tons of Fe2O3. Okay, so how do we get here? What do we do? What do we do here? So first, having not known anything, let's use this information. So we have 39.9 tons of Fe2O3. So let's try to find out the moles of this Fe2O3. That's going to be mass over molar mass. So let's say 39.9 is our mass. 39.9, we're taking it as our mass over Fe2O3. So they've given us the AR values. So that's going to be what? That's going to be 55.8 plus, and that's two of them, so 55.8 twice, plus 3 times 16. Okay, so when you add this all up, this gives us the MR of Fe2O3, which is 159.6. So 159.6 we're going to put here. That's our AR. This gives us what? This gives us 0.25 moles of Fe2O3. So we know that we have how much? 0.25 moles of Fe2O3, right? And we can also see that to find how much iron, we need to find how much of this we have. So we can see this is a 3 to 2 ratio, right? 3-2 ratio. So what I would do, I always make this x, and I'm like, okay, so 3 to 2 is here, and 0.25 to x is here. Now we just cross multiply, so we will get 3x equals 2 times 0.25. So x equals, so that's 0.5 over 3, and that's the same thing as saying 1 over 6. So I'm just going to stick to 1 over 6. So that's supposed to be 1 over 6 moles. Okay, so now we know this is 1 over 6 moles, right? We know that this is 1 over 6 moles. So this also has to be 1 over 6 moles, right? Because we're taking this Fe3O4 and in step 2. Okay, so we have to times by what? We have to times by 2 here, times by 3 here, because we have 1 to 3 ratio here. So we have 1 to 3 ratio of the iron. So 1 over 6 times 3 gives us a half, right? So we know how many moles are we producing of iron? Half. Okay, so that's good. So we can use that information. So we know what? We know N equals mass over molar mass. And we're trying to find out what the mass of iron is formed. So let's rearrange. So that'll be M equals what? N times MR. So we know N is what? N is 0.5 moles from here, right? That we calculated. And then times by the MR of iron, which is 55.8. We get what? We get 27.9. And since we started with tons over here, our final answer will also be in tons. So how much tons did we produce? We produced 27.9 tons. So the answer, let's look at the answers. We have the answers could be A, 6.98, no. B, 30.95, no. C, that's correct. 41.85, no. Okay. Which of these solutions, question number 17, which of these solutions contain the greatest number of ions? Okay, so how do we calculate how many ions there are? We have to calculate the moles, right? And in this case, they've given us what? Volume and the concentration. And we know that N equals CV, where V is in dm cubed, right? So in this case, let's work it out. So we have 20 over 1000 times by 0.5 moles gives us 0.01 moles of KCl. And since there are two ions, so let's times by 2. This gives us 0.02. Okay, let's look at B. So that's 0.4 for dm cubed already, so we don't have to change it, times 0.03. That's 0.012. And how many ions? K and Cl, so times by 2. That's 0.024. That's already above A. Let's now look at C. So that's 10 over 1000, because in cm cubed here, times by 0.6. This gives us 0.006. And how many ions? You have CaCl2. That's 2 chlorine ions. That can be times by 3. So that's 0.018. What about D? So we have 0.15 dm cubed already, so don't have to change it. Times by 0.04. This gives us the same 0.006. How many molecules? How many ions do we have? We have 3, so times by 3. 0.018. So the greatest number of ions would be, in fact, this one, because we're timesing this by L, timesing this by Avogadro constant L as well, and by L. So it's B. The answer is B. Let's go to question number 18. So potassium chlorate decomposes on heating to form oxygen. What is the atom economy by mass for the formation of oxygen? So what is atom economy? So atom economy, if you recall, atom economy is usually the MR of what? Of our desired product, right? Over the MR of all the products. All the products. And obviously we multiply by 100. So in this case, let's look. So the atom economy should be, in this case, I'm just going to call it A, atom economy. So what's our desired? We want to work out oxygen, right? And how many of oxygen molecules do we have? We have 3 of them. So on the top, we will have 3 times. So O is 16, but it's diatomic. So 16 plus 16 gives us 32. And our total products are 2 times KCl. So this represents our 302. So on the bottom we will also have the same thing. We will also have 3 times 32. So plus 2 times KCl. So K is 39.1 plus 35.5. And then we times this by 100. So times by 100. So in this case, we will get what? We will get 96 on the top divided by, so this is also 96 plus 2 times 39.1 plus 35.5. We get 245.2 times 100. And this gives us 39.1517%. And it carries on its decimal places, but we're only interested in one decimal place, so that rounds to 39.2%, which is also an answer here. You can see over here that it's not A, it's not B, it's C, and it's not D. So the answer is C. Now moving on to section B. So we've done with the multiple choice. So question number 19, part A. We have, this question is about amount of water of crystallization in hydrated magnesium sulfate. So the value of X was determined in an experiment. So we have the procedure. Step 1. So the crucible was weighed. A spatula measure of hydrated magnesium sulfate, so hydrated means it has water in it, was added and crucible was reweighed. The crucible containing the hydrated magnesium sulfate was heated using the apparatus shown. So this is the heat being applied to the crucible with the hydrated magnesium sulfate already inside this. So after heating for 2 minutes, the crucible containing the magnesium sulfate was allowed to cool and was reweighed. Okay, so now it was reweighed. So complete the table of results. So we have mass of the empty crucible. So let's just call this 1, right? So this is the mass of the empty crucible. So this is the mass of the crucible on its own. So part 2 says, so this is the mass of crucible. So this is 1, right? And we added what? And we added the hydrated magnesium sulfate. So we added the hydrated magnesium sulfate before heating. So this has what? This has the magnesium sulfate, right? H2O. This has this, right? Then we have mass of crucible, which is over here, and magnesium sulfate on its own. So we have gotten rid of the water here. Okay, so now they're asking, what is the mass of magnesium sulfate after heating for 2 minutes? So what are they asking for? They're only asking for MgSO4. They're only asking for MgSO4. Now, I can't just give them this answer because this has what? This has the mass of crucible as well. So we have to minus it. So we have to minus what? We have to minus 24.12, take away 21.21, and this gives us what? This gives us 2.91. So this 2.91 here. Now what about the mass of water lost? So this is, so let's just call this 3, 2, and 1. So in 2 we have the water, right? And in 3 we don't. So we have to do 2 take away 3. So that's 26.71 take away 24.12. And this gives us 2.59. And you need to do both marks to get it correct. You need to write them both correct to get the 1 mark. So that's part I completed. Use these values to calculate use the results to calculate the value of X in MgSO4, XH2O. Give your answer to the nearest whole number. So what can we do here? So we know the mass of what? We know the mass of MgSO4, don't we? Is what? We know the mass is what? We know it's 2.91, right? Okay, we know that. What else do we know? We also know the mass of H2O. That's lost, right? That is what? 2.59 from above here, right? So 2.9 and 2.59. 2.91, 2.59. Okay, so let's work out first the moles. Let's work out the moles of MgSO4 and compare it to the moles of H2O. Okay, so that sounds simple enough. So the mass we got is what? 2.91 of MgSO4 all over. Now the MR of MgSO4. So we have 24.3 plus 32.1, which is sulfur, plus 4 times 16, because we have 4 oxygen molecules. And this gives us what? This gives 2.91 all over 120.4, which gives us 0.024169 mole. Okay, now let's look at what? Now let's look at the moles of hydrogen, or sorry, the water. So we have 2.59, right, of water that's lost, and that's, so H2, so that's 1 plus 1 plus oxygen, that's 2.91 divided by 18. This gives us 0.14389 moles. Okay, so now let's compare the two moles. So if we have MgSO4 here and we have the water here, we have how many moles? We have 0.02 4169 moles here, and we have 0.14389. Now clearly this is a smaller number, so let's divide both of them by the smallest number, so 0.024169, 0.024169, and we end up with what? We end up with 1 to 5.9533. So what did that conclude? What does that conclude? That concludes that how many water molecules are present here? We have, so X equals 6. So we have 6. So it should be MgSO4 and 6 water molecule that we calculated, right? So where do we get the 4 marks? We get the 4 marks from getting to this state. So 1 mark for reaching here, 1 mark for the answer, and 1 mark for getting the moles of water and moles of MgSO4. So this is 1 mark, 2 mark, 3 mark, and obviously for the answer as well. Okay, so let's go down. The correct value of X is greater than the value calculated in the previous question. So they're saying that the correct value of X is greater. So they're saying what? They're saying that they should have lost more water, right? They should have lost more water. So the correct value of X is greater. So they're saying the X value is probably greater than 6. So X is greater than 6. X is greater than 6. So they're saying more water should have been lost, right? So suggest a way of improving the method to obtain a more accurate result. So we want to lose more water. So one way we could do that, so one way could be to what? Could be to heat. Could be heat for longer, right? Could be heating the crucible until we get constant mass. That's a term they use in the Marxium a lot. Heat the crucible until the mass of MgS4 is constant. So mass of MgSO4 is constant or does not change. Both are fine. So why do we do this? It says justify your answer at the end of the result, right? So what does heating help us do? It eliminates all the water, right? And how is it eliminated? It's evaporated. So this is so that all the water is evaporated. So what are the 2 marks? The 2 marks are saying that we should heat it until it's constant. Second mark is that so that all the water is evaporated. Pretty straightforward. Let's move on to question number 20. 20 part A says, this question is about copper and its compounds. Complete the electronic configuration of Cu and Cu2+. So from the periodic table, we know that Cu has how many protons? Has 29 protons, so it should have 29 electrons, right? And Cu2+ should have 2 less because 2 electrons have been removed, so this should have 27 electrons. Okay, then it says we start with electronic configuration from Ar. So how much does Ar have? How many electrons? It's a full shell, so Ar actually has 18 electrons. Ar has 18 electrons. So all we have to do is what? 29 take away 18, that's 11, right? So copper starts with 3d10 and we want 11 electrons, so that's 4s1. That's pretty straightforward. And because that has 9 electrons, so this will have how many electrons after Ar? 9 electrons after Ar. So the answer will just be 3d9. So you need to get both these answers to get the 2 marks. Okay, now a sample of copper contains the isotopes 63 copper and 65 copper. Complete the table to show the numbers of subatomic particles in the atoms of these 2 isotopes of copper. So we already said that how many protons does it have? We said that it has 29. because it has 29 electrons, right? It's not an ion, so 29. And this should also have 29 protons and 29 electrons. The only thing that changes is the amount of neutrons. So 29, so 63, so 63 take away 29. That's 5, 1, that's 4, that's 34. That's 34. That's 63, 65 will be 2. We have to add 2 more, so that's 36. So to get 2 marks, you need to get entire row correct. So that's 1 mark and that's 2 marks. So explain the term, it's part II, explain the term isotopes using the information in the table. So how do we do that? So we need to comment on all of these 3 subatomic particles. So we have to say what? We have to say that isotopes have what? Have the same number of protons, right? You can see here protons, and electronic configuration. You can see over here electronic configuration. And what's the only difference here? But have different neutron numbers. So what are the 2 marks? Just saying that they have the same number of protons and electronic configuration. That's 1 mark. And the second mark it's to do with different neutron numbers. Okay. So part III, state why the 2 isotopes of copper have the same chemical reactions. Now, what is a chemical reaction? What is it really? This is what's a chemical reaction? It's what? The exchange of electrons between atoms, right? Exchange of electrons. Now, are the electrons changed here? In the 2 isotopes, are the number of electrons changing? No, they're the same, right? So what can we say about the isotopes? What can we say? It's pretty simple. All we have to say that they have the same electronic configuration. Hence why they have the same chemical reactions. So the keyword here is same electronic configuration. I'll give you the 1 mark. Let's move on to part IV. So the relative atomic mass of copper in this sample is 63.4. Calculate the percentage abundances of isotope 63, 65 in your sample. You must show working. So let's split them up. Let's split it up. So we have 65 Cu here. And let's split them up. And we have, let's say 63 Cu here. Now the abundances we know should add up to, okay, so and then the other box here, anyways, okay, so we know the abundance. Let's say the abundance is here. Abundance is here. And we know the abundance should add up to 100% or 1 if we're dealing in decimals. So let's just deal with decimals here. So we know that the abundance is somewhere that we don't know. So let's just call the abundance X. Let's just call the abundance X. Right? And the total must be 1. Let's say the total must be 1. So this must be 1 minus X. Right? So if you imagine if this was, let's say, 0.3, this must be 1 minus 0.3, which is 0.7 to add up to 100 or 1. Now just an example. So that's an example. So we don't know what X is, but what we do know is, right, we have 65X, right, plus 63 times 1 minus X, and we end up with 63.4, right? So this is now a simple linear equation. All you have to do is expand the bracket, so 65X plus 63 minus 63x equals 63.4. So 65 minus 63 gives us 2x plus 63 equals 63.4. So then we get what? We get 2x equals, so 63.4, take away 63, you get 0.4. So x equals 0.2. Okay, so we now know this is 0.2. And 1 minus 0.2 is what? Is 0.8. So what can we say about the abundances? What can we say? We can say that the abundance, so you can the percentage of 63 Cu is 80%, and percent for 65 Cu abundance is what? 20%. And that's our answer. Okay, so part C says, part CI, copper sulfate can be made by reacting solid copper carbonate with dilute sulfuric acid. Write an equation for the reaction that occurs. So this is a reaction between what and what? Between a metal carbonate and acid. This gives us what? This always gives us metal salt plus carbon dioxide and water. So in this case, let's look at what we have. We have metal carbonate, we have copper carbonate, so that's Cu2 plus, and then we have CO3 and two of them. So that will be Cu, CO3, two of them, and the acid is H2SO4, and this goes to metal salt. So that'll just be CuSO4, copper sulfate plus carbon dioxide, anything else, plus H2O, right? Now is this balanced? Let's look. So if we have copper carbonate, no, actually this should be copper carbonate is already 2 minus, isn't it? So let's get rid of that. Get rid of this. So copper carbonate is already, so it's CO3, and yeah, and we get, and this is the equation, CuCO3 plus H2S4. So this is the equation to get the 1 mark. Okay, so an experiment was done. It was carried out to produce dry crystals hydrated. So let's see. An experiment was carried out to produce dry crystals of hydrated copper sulfate. Was it copper sulfate? Copper to carbonate was mixed with 50 centimeter cubed, 1 mole per dm cubed. Automatically, I see this is volume and this is C. So in some case, I will have to work out the moles of this. The mass of CuSO4 5H2O is this. Calculate the percentage yield for this reaction. So what is the yield? All right, what is the yield? We know that yield is what? Yield is actual, what we get, right, over theoretical times 100. So what's their actual? Is there anything else? Is there anything we calculate of the actual? Right? Okay, so let's see what we have here. So we know the mass of copper sulfate, right? Hydrated copper sulfate, 10.87. So let's try to work out the moles of this, right? And then we'll compare. So N CuSO4 not 5H2O is what? 10.87. They've already given us the molar mass, thankfully. So that's 249.6. This gives us 0.04355 moles. Okay, so we've done that. Anything else that we need? Can we calculate? So you see over here initially that we have volume and concentration of sulfuric acid. So now let's work out the moles of sulfuric acid. Is there something we can do here? Is there something we can do? Sulfuric acid is what? So sulfuric acid gives us this copper sulfate, right? It's a 1 1:1 ratio. So that means, what does this mean? This means what? That means that the 1 mole per dm cube will also give us the copper carbonate, right? Copper carbonate should be 50 over 100, sorry, 1000 times by 1. Because this is sulfuric acid, right? It's a 1:1 ratio as well. So 1:1 ratio here as well. So we need how much do we need for copper carbonate? We need one of these to give react with one of these to produce the outcome. So 1:1 ratio here. So that means we get what? So 0.05 moles is what we end up with, right? So we want to know the percentage yield. This is what we should get, right? This is what we should get. This is the amount of moles we should get theoretically. But what do we get? We get this. So percentage yield, we can also do percentage yield of moles as well, will be 0.04355 all over 0.05 times 100 to give us 87.1. It's a big decimal, but we're on to 3 sig fig, and that's what we get. So what are the marks here to get? So 1 mark for the final here, and I'll go over again what we did here. So this is the theoretical mass of copper carbonate that we should get, of the mole that we should get for copper sulfate, because it's also 1:1 here, 1:1. This is the amount of moles we should get, right? 0.05 moles. But we end up with our actual, right, which is 0.04. This is our theoretical. So we do 1/2 times 100 and 1 for the actual equation itself. So that's our 4 marks to get. Okay, move on to question number 21. So this question is about alkenes. Alkenes contain a carbon to carbon bond, double bond that consists of a sigma bond and a pi bond. Complete the diagram below to show the areas of electron density for each bond. Label the sigma and the pi bond. So this is pretty simple. Let's do the sigma bond first. So let's draw an oval. Let's draw an oval, and this is our sigma bond. Now let's draw our pi bond. So these are like oval shape like this. We have 2 of them. So this space over here, right? This space over here is usually like this space, or like this space is our pi bond. So I would say I would label this and this our pi bonds. Pi bonds. So you get 1 mark for stating this and drawing this figure, and 1 mark for the sigma bond itself over in the middle here. Okay, so propene is an alkene. The reagents needed for 3 reactions of propene. So propene acts with steam plus acid catalyst. That's an addition reaction, right? This should give us an alcohol, right? This should give us an alcohol. Okay, acidified potassium manganate, we should get a diol here. It's also oxidation. And bromine, that's just halogenation. Okay, so that's pretty straightforward. Let's try to draw them now. So we should get what? We should get 1 OH in the middle here. So, or in the end, it doesn't matter. It's carbon, carbon, carbon. So OH here. Hide everything. So the double bond opens up, and we only add 1 OH group. And what about when we add acidified potassium manganate? We should get a diol. So the C stays as it is, the original CH3, but we get 2 of these have OH, and H here, and H here as well. What about halogenation? Are both of them added? Yes, both the bromines are added. So in similar places, so we just instead of OH here, we just swap them to Br. So in this case, that will be H, C, 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 H, Br, Br, H, 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 and H. So these are the 3 marks to get. So adding 1 OH group here, adding 2 OH groups, and adding 2 BR molecules, BR atoms. So we will get the answer. So in each box, yeah, we have drawn the structure of this product. Let's move on to II. So propene also reacts with hydrogen bromide. So give the mechanism to form the major products, include curly arrows and relevant lone pairs and dipoles. So let's draw it. So we have H, right? We have our double bond C and our hydrogen and our CH3 and our hydrogen here. So what happens to this? We know that the double bond, it comes out, right? And it reacts with what? It reacts with we have also our HBr, right? HBr. And this has a positive side and a partially negative side. And what happens to its electron? It goes to its negative side. So this goes on to form what? So we get an intermediate, right? Which is, so it opens up the double bond, right? So we have opened up the double bond. The CH3, it stays where it is. We have opened up the double bond, and also, which is very significant, that we also have a positive charge here. And this reacts with the bromine atom that we had over here that has now become a negatively charged anion. So this now jumps into this intermediate, positive carbon intermediate, and we get the major product, that is HCCH, and this is also HCH3 here, and we get our bromine atom attached. So that's our major product here. So yeah, so this is the 3 mark thing. So 1 mark for is stating that this comes out, as well as this. 1 mark for the intermediate step here, and 1 mark for the major product here. Okay, so let's move on to part C. So alpha oximine contains 3 carbon to carbon double bond. It is found in plants and has a sweet smell. The skeletal formula of alpha oximine is shown. Give the molecular formula of alpha oximine. So what you can do here is you can just count the carbons. So we have 1 carbon here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So how many carbons do you have? We have C10. Now look at the hydrogen. So this is double bonded, so it will only have 1 and 2 here, and 1, 2, 3. So this will only have 1, 1, 2, 3, 4. It's already 4 bonds are taken. This is going to have 3, and 1, 2, 3. So 1. It's going to have 2, and same thing here, 2. This carbon already has 4 bonds attached to itself. This will have 2. This will have 3. So now let's just count them. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So molecular formula is H16. Alright, so on the skeletal formula, draw a circle around the part of the molecule that gives rise to the geometric isomerism of alpha oximine. Now this at the end here cannot be a geometric isomer, because it has the same hydrogen on its either end of the bond, the double bond. So this cannot be it, and the same reason this can also not be it. So logically this has to be the answer. So when we circle it, make sure to circle the middle one over here. Now it says draw the skeletal formula of the other geometric isomer. So what will happen is that, let's say we keep this as it is, and so now this becomes, so I'm going to draw this as it is. So this, and this. But now we have switched it around, so now we will have one big one over here, and this will be this. So we've just switched the 2 ends around to get that. Okay? Alright, so So that's our 2 marks here, and that's for circling, and that's for switching. So what we have done here is basically we have swapped this end and this branch. We have swapped it. Okay, so part IV in an experiment 0.05 moles, so that's important, 0.05 moles of alpha oximine reacted with 3.6 dm cubed of hydrogen in presence of a catalyst. Deduce the structure of this product. You must show your working. So we know that it reacted with the 3.6 dm cubed, right? Now, whenever you see that it's reacting with a volume of hydrogen or volume, you should always remember that 1 mole is 24 dm cubed, right? So 3.6 over 24 will give us the moles of hydrogen that was being reacted. So that's what that is, 0.15 moles that of hydrogen that's been reacted. And we actually only started with 0.05 moles. Now what happens when we react this alpha oximine is that with this hydrogen, that these double bonds will now open up. When double bond will just open up, right? So it'll be a saturated alpha oximine chain. So let's see how that would look like. So in this case, what did we start with? We have 0.05 moles of what? Of the alpha oximine, right? And it reacts with 0.15 moles, so that's 3, right? That's if you think about it, when you compare it to 0.15 moles, we have a ratio of 1 to 3. So this alpha oximine is basically reacting with 3 moles of hydrogen in comparison. So 3 double bonds of carbon react with hydrogen, so all double bonds are gone. All double bonds should be gone. So what would that look like? So if you just look here, all double bonds are gone, so all it would look like is look like this. So here, 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 here. So this is what it would look like. So that's our two marks for getting 1 to 3 ratio, 1 mark for structure, and that's it. So let's move on to question number 22. This question is about bonding in the elements and period 3 in the periodic table. The melting temperature of period 3 elements are shown in the table. Sodium, magnesium, aluminium metals. So state is what is meant by metallic bonding. So this is pretty straightforward. All you have to say that it's what? It's the electrostatic attraction between cations and the sea of delocalized electrons. So all you have to say is that attraction between, not electrostatic, I think that attraction between cations and sea of electrons. Instead of electrons, I think it's better to put delocalized. It's always a good word to put there for when you talk about metallic bonding. Delocalized electrons. So that's 1 mark, just stating the attraction between cations and the sea of delocalized electrons. Melting temperature depends on the strength of metallic bonding. Explain why metallic bonding in magnesium is much stronger than that in sodium. Now this is very simple. Now what charge does Na have? It has a what? It has Na plus charge, and Mg has 2 plus charge, right? So we already know that magnesium has a higher charge, and because it has a higher charge, it probably has a smaller ionic radius. What else do we know? That it probably has more electrons, right? Because it's going down the period, going across the period, you get more electrons as well, right? Because you have more protons, some more electrons to balance it out. So what can we say? We can say Mg 2 plus has a higher charge as well as a smaller ionic radius, and also has more delocalized electrons than sodium. That's it. So all you have to say is, we talk about a higher charge, small ionic radius, and has more delocalized electrons. That's it. They give you all the space, but you don't have to use all of it. You can just get the answer in a couple sentences, and it's fine. It's part BI. In the elements silicon, phosphorus, sulfur, and chlorine, the atoms are joined by covalent bonds. Now this is where you would write electrostatic attractions. Describe the attraction between the atoms in a covalent bond. So you would say, this is the electrostatic attraction. Electrostatic attraction. So it's between what and what? Electrostatic attraction between what? Between the shared electrons, right? That's what covalent bond is. Shared electrons. And what? The nuclei of the other bonded to atoms. So, and the nuclei, which is basically the center of the two bonded atoms. So electrostatic attraction between shared electrons and the nuclei of the two bonded atoms. So explain why the temperature of silicon, right, is much higher than that of phosphorus by referring to their structures. So what do we know about, what can you remember about silicon is that it has a diamond-like structure, right? Diamond-like structure. Now what kind of structure is that? Now that is a giant covalent structure, right? So what can we say? So we can say silicon, right, is what? Silicon is a giant covalent structure, right? Whereas phosphorus is just a simple covalent structure. Whereas phosphorus, I'm just going to write P. Phosphorus is a simple covalent structure. Okay, so but we haven't talked about why its melting temperature so much higher, because now we're going to talk about it. Because this means what? This means that when silicon melts, so in this case when silicon, so Si melts, so strong covalent bonds are broken. So strong covalent bonds are broken, whereas bonds are broken as opposed to, whereas for phosphorus only London forces are broken, P. London forces are broken, which is easier to break by far, right? Forces are broken. Okay, so let's look at what we have said. So giant covalent structure, that's 1 mark. Saying that P is a phosphorus is a simple covalent structure, that's 2 marks. And explaining why that since silicon is melting, we're breaking covalent bonds, and P is breaking London forces. That means, so we can expand on this. We can say that. So it's harder, or not say harder. It requires more energy. To break covalent bonds than London forces. So now we have explained why it just requires more energy, hence why it's a greater melting temperature of silicon. So let's move on to part CI. Sulfur reacts with chlorine to form sulfur dichloride. complete the dot and cross diagram of a molecule, sulfur dichloride. Use dots for chlorine and crosses for sulfur. Show the outer electrons only. This is very forward. We know that chlorine has only how many? Has only 7 electrons, so that's pretty straightforward. So let me put this more to the top here, maybe. There we go. Same thing here. And here. And let's do the other one in purple, so in pink. So we have our sulfur, right? So it says suggest. So the next part says suggest a value for Cl SCl bond angle. Justify your answers. So now let's look at how many bonding and lone pairs we have. So we have a bonding pair here and bonding pair here. So we have 2 bonding pairs and we have 2 lone pairs, right? So we can say over here that it SCl has 2 bonding pairs, right? And 2 lone pairs. So because we have 4 pairs of electron, right? So we know that 4 pairs of bonding. So or we say 4. Let's say 4 bonding pairs is a tetrahedral shape, right? Tetrahedral shape. And that gives us what? That gives us usually 109 degrees, 109.5 degrees, right? But since we have 2 lone pairs, so because of the 2 lone pairs, we have to subtract. We have to minus 2.5 twice. Because of the repulsion, right? Because of the repulsion. So in this case, the repulsion will be minus 2.5 twice. So 109.5 take away 2.5. This should give us what? So it's minus 5. So that's what? 104.5, and that is the answer. There's a range of answers, but it's ranging from 103 to 105, but this is what you want to get. This is the logical way of thinking about it. Okay, so saying that has 2 bonding pairs, lone pairs, and then explaining why there's repulsion gives us 3 marks. So now moving on to question number 23. So we have, this question is about ionization energies of the elements in period 2 of the periodic table. The first ionization energy of the period 2 elements are shown. So this is what we've shown. Give an equation that represents the first ionization energy of lithium, includes state symbols. So the first thing we need to remember is that all the time ionization energy is always in gaseous state. Always, we need to remember that. So Li, always in gaseous state. And this goes to Li plus, right? Still gaseous state, plus E minus. So that's our 1 mark. So explain why there's a general increase in the first ionization energy across the period, right? Across the period. So what's happening across the period, right? What's happening across the period? So as we go from here to here, what's actually happening what's happening as we go across the period? We are increasing the protons, right? Increasing number of protons, right? And because we increase the number of protons, what's happening to its effective nuclear charge? It's increasing, right? It's increasing its effective nuclear charge, and we're getting a smaller atomic radius. So what can we say? What can we say over here? What can we say? We can say over here, since or we can just say across the period, the number of protons are increasing, right? That we know is correct. So what happens when we increase the number of protons? There is a greater attraction, right? So there is a greater attraction between the nucleus and its electrons, the nucleus and electrons. That's it. So 2 marks. So you're saying that the number of protons are increasing, so that means there's a greater attraction or greater effective nuclear charge between the nucleus and electrons. So let's see what it says. Explain why the first ionization of oxygen is lower than that of a nitrogen. Okay, so now let's go back to the original. So we can see there's a dip here, right? There's a visible dip here between N and O. That's actually to do with the electrons. Now let's write the electron configuration of O to illustrate what's actually going on here. So that is what we have: 1s2, we have 2s2, then we have 2p4, and for N we have 1s2, 2s2, and 2p3, right? 2p3. So in terms of spin, let's explain it. Well, the spin. So this has, so we have, how many here? We have 1 here, we have 3, and we go back here, and we have a spin here. And for N, oh wait, let me change that. Okay, same thing here. We have 1 electron spin. So what can we say? We can say that this is less stable, right? Because it has one, only this has one more electron, right? And it's spinning in the opposite direction. But so this is more stable, right? So what can we say? We can say that it's easier to remove electron from 2p orbital from oxygen, right? Since it's full, right? You see this is full, right? Over here this is full, this is full. So since it's full, so less energy is actually required, because there's, you know, it is repelling away, right? Spin repulsion. Less energy is required to remove what are we talking about? Remove a paired electron. That's it. Hence why the ionization energy of oxygen is less than nitrogen. All right. Okay. So then we talk about that. Let's go on to part B. So all the successive ionization energies of nitrogen are shown below. So 1, 2, 3, 4, 5. Whoa, big graph from 9 to 53. So what's happening here? So explain the trend in successive ionization energy. So it's definitely increasing, right? So you know, the ionization is still increasing. Why? Because we're taking away, it's becoming more positive. So the IE, ionization energy, increases, right? Increases because the ion is becoming more and more positive, right? The ion is becoming more because ion is becoming more positive, and that requires a lot of energy, becoming more positive. And what about this jump from 9 to 53, which is a big jump, right? What's happening? And so this big jump is probably what? We're removed, this 6th electron is probably removed from a new shell, and that there is a significant jump between 5 and 6 due to what? Due to 6th electron is removed from a new shell. From a new shell which is already stable, right? So it's hard, it requires more energy. So what are the 2 marks? The 2 marks are saying that ionization increases because ion becoming more positive, and that the 6th electron removed is from a new shell. Okay, let's move on to question number 24. So, 0.210 gram of sample of volatile organic liquid is injected into the gas syringe and heated in an oven. At 100 kPa and 358 Kelvin, the syringe contains 72.5 centimeter cube of gas. Calculate the molar mass of C. We have been given the equation, so all we have to do is work out. So let's see what we have to do here. First things first, the volume has to be in meter cubed. So we have to 72.5 divided by 10 to the power 6, or same thing as saying 7.25 times 10 to the power -7. Same thing, right? Oh, sorry, negative. Or let's just keep it simple. 72.5 times 10 to the power -6. That's it. Okay, so let's rearrange. We want the molar mass, right? So N equals PV over capital RT. So what's P? P is 100 kPa, so 100 times kilo, which is 10 to the power 3, times by 72.5, that's our volume, times 10 to the power -6, all over RT. So RT is, so R we know is 8.31, multiplied by T. So what's T? T is this temperature over here. That's our T, 358, and it's in Kelvin. So that's pretty straightforward. So they've given us all the information. So this gives us, what, 2.437 times 10 to the power of -3 moles, right? So what do we do with this information now? Because they've given us something else, haven't they? They've given us this mass over here. So we can work out its molar mass, right? How do we work it out? We know N equals mass over molar mass. So MR equals mass over N. So mass is 0.210 divided by 2.437 times 10 to the power of -3, and we get what? We get 86.172. So let's round it up. So MR is what? 86. So that is the MR, right? So that's how we get 4 mark. 1 mark for 86, 1 mark for getting the moles, 1 mark for converting this, and 1 mark for the equation itself. Okay, so that's 4 marks. Now it says the organic liquid is a hydrocarbon. Give a possible name or formula for C using the answer in A. So we know that the MR is 86, right? And we know it's a hydrocarbon, so we know it's C and it's gonna have hydrogen. So let's just see how it would work. So we have CH3 over here, right? So we have CH. So that's what we know. It's carbon is 12 and we know hydrogen is 1, so that's 15. Okay, so we keep adding on hydrogens until we get 86, so that's 14. So 15 plus 14 is 29, and then we keep adding 14 until let's say we get 86. We should get 86 at some point. So at 14, that's 33. Add another 14. That's another 14. That's what? 47. Another 14. That's adding another 14. That's what? That's 61. And then let's add another 14. That's 70. That's 70. Oh, did I add it correctly? Let's see. 15 plus 4 is 29. 39 plus 10 is 39. Oh, that's 43. My bad. See, made a mistake here. So 29 plus 10 is 39. So that's 43. 43 plus 10, 53 plus 7, 57. And then this is 57 plus this, that is 61. 61? Yes. Okay, so let's say we're adding another 14 here. And what do we get? We get 70. Let's just double check. That's what. So 15 plus 14 is 29, plus 14 is 43, plus 14 is 57, plus 14 is 60, 71. See, I made another mistake here. That's 71. Add another 14, you get 85. Okay, so what if we add another hydrogen here? That will give us 86. So our name, or we have done the formula anyways, it's this, is hexane. Because we can see how many carbons, 1, 2, 3, 4, 5, 6 is a long chain. So it's hexane. So the answer is hexane. Thank you so much for watching the video. Be sure to like, subscribe, and share, and join the Discord where there are people helping out. And thank you so much for over 500 subscribers and 600. I'll be hoping to help you guys as much as possible. And until next time, thank you.